Hello, my name is Nuno Martins, and I am going to present my work with Bernardo Marques, Paulo and Beatriz Santos entitled Seeing Clearly, a situated air quality visualization with augmented reality egocentric viewpoint extension. The outline of this presentation includes the following sections: Introduction, Related Work, Augmented Reality Application for Air Quality Situated Visualization, User Study, Results and Discussion, and Concluding Remarks and Future Work. Air pollution is a significant problem that adversely affects the health of people around the world. According to the World Health Organization, nearly the entire global population breathes air that exceeds the recommended guideline limits. As illustrated in the figure, air pollution was the fourth leading cause of mortality worldwide in 2019. Despite the availability of information, raising public awareness about air quality remains a challenge. To change routines, it is crucial to focus on everyday tasks and living areas. Technology can play a vital role in increasing public awareness of air quality. For instance, augmented reality, AR, enables users to access and interact with both digital and real-world content, while situated visualization, SV, emphasizes visualizations that are contextually relevant. For a better understanding of the work, it is necessary to present the main challenge when combining SV with AR, the user's egocentric viewpoint limitation. The egocentric viewpoint in AR refers to the user's perspective, which is determined by the position and orientation of their device. The challenge lies in the ability to perceive and gather information beyond the current viewpoint while minimizing and eliminating the need to physically reposition the device. To address this limitation, there are two main techniques commonly employed: multi-perspective rendering, which involves adding additional views of the real world to extend the field of view, and transitional interfaces, which allow for seamless switching between AR and VR contextualized viewpoints. Regarding the air quality research, we can categorize relevant studies into three main groups, represented by the following examples. First, AirLens, an interactive visual analytics system designed to assist specialists in comprehending the evolution of air quality in urban areas from various perspectives and levels. Second, Copernicus Atmosphere Monitoring Service and Lotto Zeros are web-based applications that offer accurate and reliable information on air quality and climate change to the general public. Lastly, Air Transformed, and Breezometer are examples of more focused AR-based mobile applications that allow users to visualize air quality levels in their immediate surroundings. However, it is important to note that none of these AR solutions specifically address the issue of the limited egocentric viewpoint of the AR camera. After conducting a focus group discussion involving environmental experts and AR specialists, as well as the outcomes of a survey of related works, the following requirements for developing an AR app for air quality SV have been identified. Mitigate the egocentric viewpoint, use air quality data from reference agencies, use simple animations for AR impact, allow GPS-based selection of displayed air quality data, provide explanation and related information, perform simulations, and follow visual representation recommendation. For instance, interactive and user-friendly visualization, concise label and legends for all visual elements, and intuitive and meaningful color scales. Having in mind the previously mentioned requirements, the situated pollution application was developed in Unity, with Vuforia and Google Maps SDK for Unity libraries. Uses two different solutions for mitigating egocentric viewpoint limitations, the side-by-side dynamic AR and VR camera feeds, and the multi-dynamic camera feeds. Uses air quality data gathered by the Environment and Planning Department of the University of Aveiro, which is displayed according to their GPS location. Allows navigation on the 3D map, allows simple simulations, employs a simplified color code and numerical scale, green, yellow, and red for good, moderate, unhealthy, and very unhealthy hazardous pollution levels, and uses a different representation of pollution concentration, spheres, planes, or molecular models. The sphere size varies based on pollution concentration levels. An exploratory user study was conducted to evaluate the performance of the proposed solutions for mitigating egocentric viewpoint limitation in a realistic environment. The study took place in a public space between two streets using two distinct methods on a Samsung S21, the AR interface only and the AR plus 3D map based on the side-by-side dynamic AR and VR camera feeds proposal. The participants' task was to retrieve the GPS coordinates of the location with the highest pollutant concentration along the path with lower pollution levels, out of two given options. They performed this task first with the AR method and then with the AR plus 3D map method. To ensure safer navigation in the streets, participants could utilize the multi-dynamic camera feeds proposal. The task was chosen to mimic a scenario where informed decisions about the least polluted route could be made. The procedure used in the study was as follows: explanation of the study and obtaining informed consent from the participants. Time allotted for participants to familiarize themselves with the application and receive instructions. Task performance, with an observer recording vital data on the participants' actions. Completion of a questionnaire, followed by a brief interview to gather participants' opinions of the proposed prototype. The participant sample consisted of 7 individuals with diverse characteristics, including age, gender, education, and occupation. The recruitment process involved reaching out to known individuals. All participants were new to air quality visualization with varying degrees of experience with mobile applications. Only one participant had prior experience with AR. The measurements collected included time taken to complete a task, response accuracy, self-reported experience, and effort. The results obtained from the study are shown in the following figures. The figure at the top left presents the disaggregated data regarding the ease difficulty of the task. Overall, the participants consider the task easy, specifying that it was easier when using the AR method. The effort required to complete the task with AR method was due to GPS instability, 3 participants, obtention to information, 2 participants, and lack of experience with mobile application, 1 participant. On the other hand, the effort required to complete the task with the AR plus 3D map method was due to lack of familiarity with the application, 2 participants, GPS instability, 2 participants, and difficulty in combining data, 1 participant. The figure at the center presents the disaggregate data regarding the differential of GPS coordinates obtaining in meters. The average differential between the two methods was 7.29 meters. The figure at the bottom right presents the disaggregate data regarding the task duration in seconds. The average duration was 382 seconds and 159 seconds, respectively, in AR method and the AR plus 3D map method. Comparing the two methods, the participants said that the most comprehensive one for completing the task is the AR plus 3D map. Regarding the most useful and preferred method, 14.29% of the participants vote for the AR method, while 85.71% voted for the AR plus 3D map. Concerning the most practical way of performing the task, 42.86% of the participants voted for the AR method, while 57.14% voted for the AR plus 3D map. The advantages of the AR method, according to the participants' answers, are that it is practical and familiar, 1 participant, offers relevant real-time information, 3 participants, and requires less attention, 1 participant. Its disadvantages are less information, 2 participants, GPS instability, 1 participant, and being more laborious, 3 participants. The advantage of the AR plus 3D map method, according to the participants' answers, are that it offers more information, 7 participants, and provides a better understanding of the severity of the pollution, 1 participant. Its disadvantage is the difficulty in coordinating between the interfaces, 2 participants. The left figure presents the disaggregate data regarding air quality information. The values obtained in its first 2 ratings ease of understanding the information and complexity of the information validate each other. The response obtained regarding the participants' sense of involvement highlights the usefulness of AR technology in alerting to environmental issues and creating a strong connection between users and the provided information. The right figure presents the disaggregate data regarding the representation of pollutant concentration levels. As can be seen, participants understand the representation of pollutants better when spheres are used, as they change size depending on the concentration levels. The lower score obtained in the representation used in the AR camera is due to the complexity of the 3D molecular model used, which was not very perceptible to all participants. Regarding the multidynamic camera feeds proposal, the participants only used this feature to cross the roads more safely because their primary focus was on viewing the air quality data and walking on the path along the sidewalks. However, the general opinion was that this feature would be very useful in increasing safety, providing a greater field of view, and giving a sense of social presence. Concerning the situated pollution mobile application, participants classified the application as simple, intuitive, interesting, and easy to understand. They found it useful for everyday life and relevant for changing behaviors related to air quality, such as deciding to walk instead of driving to reduce pollution. though one participant felt that the intended purpose of the application was unclear. To conclude, an application based on SV to increase air pollution awareness was created with two solutions to mitigate the egocentric viewpoint limitation. An exploratory user study regarding the use of the created application was done. The study's preliminary nature focused on gathering feedback, not providing hypotheses. Its results indicate that the proposed solution seemed to enhance user access to information. Participants reported feeling better informed, safer, and saving time when using the AR plus 3D map method. The future direction for our work are improve the application, make a larger scale study, and incorporate artificial intelligence and analytic tools. Finally, air pollution is a pressing global issue that affects millions of people worldwide. Therefore, it is important to increase awareness and implement educational interventions to address air pollution effectively. Thank you for your attention.